Hi everyone, welcome to another lesson where we're investigating probability and applying all those cruel rules, probability rules, to a number of situations where we can start to predict what the chance of certain events are going to take place, what that chance is going to be. Now, remember that we can represent these probability problems using a Venn diagram. That's the focus of what we're going to be doing today. So have a look here. In today's lesson, we're going to focus on Venn diagrams. And in particular, we're going to explore the rules that we've already established, the addition rule, which we also say is the OR rule, the multiplication rule, which we haven't done very much of, which is known as the AND rule. We're going to look at mutually exclusive events, complementary events with the complementary rule, and then we're going to introduce these ideas of independent events and dependent events. So I can't wait to get going. Let's have a look at a Venn diagram. Notice on this classic Venn diagram, we have the sample space represented at S and X that is representing those events that are the favorable ones. Remember to calculate the probability. It's the number of elements of those in X divided by the total number in the sample space. And that's a very important rule for calculating theoretical probability. What else is very nice about this Venn diagram? It introduces to us the idea of those elements that are not in X. In other words, the ones that aren't the favorable outcomes. Do you remember what we call those? Well, have a look. The blue section represents all the elements of the sample space that are not in X. We can say that that is the complement of X. This is equal to not in X. And so the complement is very useful, and we can use it to solve very many different problems using the complementary rule. So please make sure that you understand the complement. There's one other thing that I want to just mention here, is if we look at X and its complement, what do you notice? Is there any intersection? No, you can't be in X and not in X at the same time. So what do you think we would call those two sets, X and not X? Well, they are mutually exclusive. If we've chosen X, we're excluding all those elements that are not in X. That's why we're saying it's mutually exclusive. It's excluding those not in X. I hope that makes sense. So let's just summarize that result. And we can see that in a complementary event, we know that X means that X prime or X dash means not in X. They cannot happen at the same time. And we notice that these are mutually exclusive events. Here's another representation of mutually exclusive events. Here we have two mutually exclusive events, X and Y. Notice that there is no intersection. That the intersection of X and Y, the number of elements in that intersection is 0. And that's why we can say they're not intersecting. There is nothing, if you're in X, you can't be in Y. There is no overlap between these. And that's why we say these are mutually exclusive. Do you remember how we calculate the probability of X or Y when they're mutually exclusive? This is the addition rule, the OR rule for mutually exclusive events. Well, have a look. We recognize that those events are mutually exclusive because there's no intersection, and we can say the OR rule, X or Y, is simply the probability of X plus the probability of Y. So it's the addition rule. So remember that when we have OR, we must remember that we add. And that's very important. Now, we've illustrated that for 2 events. Do you think it will apply for 3 events that are mutually exclusive? Well, have a look at the Venn diagram. There we go. We've got the Venn diagram of X, Y, and Z, and you'll notice that those do not have any overlap in them. There is nothing in X that is in Y, and nothing that's in X that's in Z. So these are mutually exclusive. And for that reason, if we wanted to find the probability of X or Y or Z, okay, all of those, then we would look to see if we could contain all the elements in X or in Y or in Z. It doesn't matter whether they're in X or Y or in Z. We're only worried about that they must at least come from one of those sets. If we were going to calculate that, we would extend the addition rule, and this is what it would look like. Because they're mutually exclusive, notice there's no intersection. Extending the addition rule, it's simply adding those probabilities together. Now, notice when we do that, you can see the scope of the OR is represented by the orange shading. All of those elements. So at least the elements are either in X or in Y or in Z. There are many of them. Don't think that OR is restrictive. OR means more, okay? It means more. It can be in X or in Y or in Z. People get very confused between the or and the and I want to make that very clear again, that or means more. Please try and remember that. Now, if we go on and have a look at these sets, recognize first of all that we've got X and Y and they are intersecting each other. There is a common element in the intersection. So we can immediately say that the intersection of X and Y is not equal to 0. So X and Y in this case are not mutually exclusive. They're not mutually exclusive. And again, if we are going to apply the OR rule, in other words, the addition rule, we need to recognize here that we've got to take into account the intersection. The element that was in X and the element that was in Y would be counted twice. So say, for example, there was a 4 here and a 4 here. If we add those probabilities together, we'll have too much. We have to take away the 4, the probability of the 4 in this one. So it undoes those things and prevents us from counting twice. When we say or like that, remember we're including everything. And so the picture on the Venn diagram looks like this. Here you can see in the Venn diagram, we've represented all the space shaded in blue. And so this is what we're doing when we ask for the number of elements in X or Y. And this helps us also then to apply the addition rule to calculate the probability of X or Y. In this case, we've only shown 2 sets that are intersecting, but we could add a third set. Look what it looks like. In this case, we've got X, Y, and Z. Notice that we have 4 different types of intersection. In fact, we've got the intersection between X and Y. So that is the intersection between set X and Y. This is the intersection between set Y and Z. And this is the intersection between X and Z. And what do you think this area is representing over there? Well, I'm sure you can figure it out. It is the common intersection of all those sets. It's where there are elements that are common to X, Y, and Z. And so we need to get a picture of these Venn diagrams when we have more than 2 and recognize there is more than 2 different types of intersections. Sometimes it's only the intersection of 2 sets, But there's that third one, the middle one, that's the intersection of all three. And in this way, we can describe it and summarize it as follows. We can recognize that there is an element in the intersection between x, y, between x and z, z and y, and there's an element in the intersection of all three of them. Because of that, these are not mutually exclusive. And that's very important. When we look at these and we say, well, what's the area that represents at least one element in x or y or z? It will be that whole area as represented there. And so we're going to do some investigations to look at establishing from data that has been collected in the field what these intersections could be and what the probability of certain events taking place. These are quite fun, and I'm looking forward to going through some with you. Let's just move on to one other concept. We recognize in this situation that the focus is on the intersection between x and y. And we want to ask about the nature of that intersection. What I need you to understand is that there are two types of events. Events which have an intersection, they are not mutually exclusive. So they are not mutually exclusive. They do have an intersection. In this case, the probability of x does not affect the probability of y. And for these type of independent events, the rule is given that for that intersection, we can calculate the intersection as being the probability of x multiplied by the probability of y. Now guys, this only happens for independent events. It's very important that you understand that the probability of the second event, or the y event, if you like, is not going to be affected by the x. They would be the same sort of calculation. There's no influence of the one on the other. But if there are dependent events, choosing one thing can affect the second one. The outcome of the first event can affect the probability of the second. And those are known as dependent events. And we summarize them very simply as follows, that again, they're not mutually exclusive. There is something in the intersection, but we recognize there's an influence, and this identity doesn't hold. We recognize you can't multiply them together and find what's in the value of the intersection. I think, you know what? It's time for us to do some practical applications of these. And there's some very important rules for dependent and independent events that we're going to discuss as we go further. But please remember, this is part of the multiplication rule. Let's go on. So in this question that we've got two events, A and B. And we're told that the probability of A is 0.48, that the probability of B is 0.26. We're asked to determine what is the probability of A or B if A and B are mutually exclusive. Well, that's a giveaway. I'm sure you've got it. Think about how you would answer the question, and let's get ready to give you the answer. Here we go. So my strategy for answering this question is first of all to look at the Venn diagram. Because I'm told they're mutually exclusive, I recognize that I'm going to draw A and B as disjoint sets. They're not overlapping. There is no intersection. And so what we can say is, if we're wanting to find what is the probability of an element being in A or in B, it's the shaded area in both of those sets. And we recognize, because there's no intersection, that the probability of A or B is equal to the probability of A plus the probability of B. Remember, if they were not mutually exclusive, then we would have to subtract the probability of the intersection. But we can see here, the probability of the intersection is 0 because there's no element in the intersection. And that's how we apply the OR rule, the addition rule for mutually exclusive. Let's do it very quickly. We're going to say it's 0.48 plus 0.26. And if we do that, we'll get that is 0.74 at least. And we have calculated the probability of A or B. Let's have a look at the next part of the question. The next part of the question says that we are asked to find, tricky, the probability of not A and not B if A and B are mutually exclusive. So here it's a little bit tricky because it's the complementary rule. But actually, you know what? It's not so harsh. We just have to take it step by step. And remember, there's more than one way to solve this. So I'm going to do it in one particular way. See if you can find another way. And we'll see if we can get that answer as well. So the way I start this problem is to say, if I'm looking at the probability of A as being given, why don't I find out what the probability of the complement is? And remember, the probability of the complement is 1 minus the probability of A. So in that respect, we can see that this probability of not A is 0.52. And if I were to shade that, I would shade all this area that isn't in A, including B. How about that? I would have to shade B as well. Now, if I recognize that that would cover the whole sample space, notice I'm not covering A, I'm only covering what's not in A. And I've got the probability of not in A. Now, what about B? I'm going to change the color of my pen so we can see it. And we're going to say, what's the probability of not B? Well, that's everything that is not in B. And we're going to recognize that as 1 minus the probability of B. And if we do it, we recognize that that is going to be that's 1 minus 0.26. That's going to be 0.74. Agree? You recognize that if you add those two together, 0.26 plus 0.74, you're going to get 1. And that's the test to make sure that you've got it right. Now, if we were to shade not B on the Venn diagram, notice what I'm doing. I'm going to shade everything that is excluding B, including A. So if I'm going to say, what is the probability of not A and B? Well, that means I've got to find the intersection of not A and not B. So what are the elements that are not in the intersection? Can you see that the things that are common, that have a blue and a red shading on the diagram, those are the things outside of A and outside of B. In other words, it's this area in the sample space that I've indicated here. So it doesn't include A. The overlap, the intersection, is simply the parts that are not in A and not in B. So intersection is what we're looking at here. There is an intersection. We just need to make sure that we're only counting those that are in the intersection. And so I could carry on and do this calculation and apply the AND rule, but there's the shorter way to do it. The shorter way is to say to myself, if I'm wanting the things that are not in A and not in B, then all that I'm going to do is I'm going to say, let's take 1, and I'm going to subtract A, and I'm going to subtract the probability of B from it. So what I'll be left with is the part that is shaded blue and red. I hope you can see that. Now, you can go and test the rule for intersection. Remember, there are common elements, and these are not mutually exclusive. But in the calculation, let's do it quickly so you can get your answer. So we recognize this one was 1, this one was 0,48, and this one was 0,26. So if I recognize what those all add up to, I'm running out of space, so I'm just going to put it over here, up at the top, to get my final answer. And what I'm going to do is I'm going to say I recognize that that is equal to 1 minus a total of 0,74. Okay, that's the total. If I've added 0.48 and 0,26 together, that will give me 0.74, and the complement of that is going to give me 0,26. So there I've got the probability of choosing something that's not in A and not in B. In other words, it's in the sample space. It's not in A, it's one of those unfavorable outcomes. Let's move on. Last question that we're going to do is we were asked to do this and say, if we've got B and A together, we want to find the probability if they're independent events. Now, do you remember what the rule for independent events is? Well, that's right. It's the multiplication rule. So very clearly what we've got to do here is we recognize there's an intersection. Yes, there's the intersection, and that's what we're trying to find. We're going to say the intersection of A and B is equal to the probability of A multiplied by the probability of B, which is equal to 0,48 multiplied by 0,26. Guys, I'm sure you can get your calculators out and check that you've got that. That's what we would do for independent events. I think it's time to take a little break. After the break, we're going to explore some more Venn diagrams.